welcome to Embedded Internals. This is third episode of our series, Memory Thinking series. Stack internals explained in depth detail. Let us start by running a simple code. This is our simple code in which from the main function we have called the function show address 3 times. Okay. In the show address, we have a local variable named x, and we are just printing the address of that variable and returning 0 on success. Let us see the output. See, we have every time the function call is made, we find that the address remains same. So 3 times function call is made and 3 times the function address remains same. Okay. So how can a variable disappear and then come back at the exact same address? Because once the return is called, we releases the stack frame. So the second time, so address will be called, a new stack frame will be allocated. So ideally there should be a different memory. Why the same memory address is returned second time, and similar not only second time but third time as well. If we will call 5 times, we will see the every time a new same address will be returning. So today we will go inside the stack, the memory system that powers execution itself. So the question arises, why function call need memory? So when a function will execute, like when we have a RAM in the virtual memory address space, in the stack segment, whenever a function call will be made, like the main has its own stack frame, this will store the local variable of this function, local variable, return address, saved registers, etc. Okay. So main has its own details. So whenever a new function call we made from the function, it requires its own stack. Like here the saved address is called saved address. So this function will also have its own local variable, return addresses, and saved register and everything. So we need a function frame so that we know that for that particular function, where do local variables lives? Where is the return address stored? How does CPU know where to continue? And what happened during nested calls? So every time a new function will be called, a new stack frame is added. Okay, so we can say that stack is a continuously changing memory region. 100 of function call is being called and returned, the 100 of time the stack has been expanded and released. Okay, continuously changing memory region. And what it is tracking? It is tracking the active execution state. What we say tracks, what the stack will going to track? It will track the local variables. So first is active function call, local variables used in that function call, return address of that function call, and CPU states or saved CPU state. For all these things we call it execution memory. What is stack frame? A stack frame is the memory region representing one active function call. And when we say active call, means every function call will get, so here it is a function call, it will get its own frame, temporary execution state, and isolated local execution context. We can say it is context, execution context. When we say context, we means a local variable, return addresses, saved address registers, all those things. And we have a local state as well. Let me show you from the terminal one small example. I hope you remember the first function. Just have a look at this function. It's calling the function show address 3 times. Okay. we have one more function, demo4 code, where we have the main function in which we have declared one local variable and calling a function foo. Similarly, from the function foo, we have declared a local variable x and calling the function bar. Similarly, from the function bar, we have declared a local variable z and return the address. Okay. So just have a detailed look on this and on the first program as well. In the first program, from the main function, we have called one function show address 3 times. In the show address, we have just declared a local variable and printed it address. Okay. So what is happening in both the case? In the in the first case, demo 1, you will see same address 3 times, whereas in the new program we see different addresses every time. Main is at this address and foo is this address, bar is this address. And one more thing you will observe, that we are getting the address from the lower region. So main is at 36b f4 f, this is d4, this is b4. So we are stack is growing downward. Okay, let me show you once. 3d14 c f4 c d4. So this shows the growth of stack is at the downward direction. So this time we are getting 3 different addresses, and in the first case we are getting similar address for 3 calls. What is different happening at this time? Let me show you. In the first case, where from the main function, when the main function will be called, a new stack frame will be allocated. Okay, which have the memory space for local address and the return address. Okay, and it is calling a new function show address. So when this function call is made, we will have a additional stack frame corresponding to that. So this stack frame has a local variable int x stored here. Let us suppose this stack frame is at 100 to this particular address. Okay, and the return state and the CPU state, return address and CPU states. So we have called, and then after printing the value, this stack frame is, we have deleted the stack frame. Okay, this is not calling any function, it returns back to the main. So when it returns, this stack frame will be deleted. Okay, so once at calling it is created, and once at the returning it is deleted. Here it is created, here it is deleted. Once the deleted, this memory will be free. Okay, after deletion, memory free. So again, when we are calling the show address, okay, again a new stack frame will be created. This is already deleted. Okay, forget that. New stack frame of show address will be created. This is show address. And it will get got the same address space, same memory address, this because after deletion memory is free and our stack reuses the memory, reuses the same memory. So here memory reuse, free memory reuse. That is the reason we are getting the same address for the three executions, 3 functions call. Okay, and again if the new function, once it return, this stack will be deleted, stack frame. And once again we are calling a function call, then again a new stack will be created and it also get the, as this address is free, we got the this address again. So we can say we are old frame is getting destroyed, but same address space can be reused. Okay, so in this case we have seen after the function returns, after the calling function returns, old stack frame or function frame got deleted. Old function frame got deleted or destroyed. Same stack space is reused because we have a limited stack space. We reuse the same stack space for the new function call. Okay, so first time our show address is called, and after it returns, the function frame corresponding to the first call of the show address space will get destroyed. However, the address it is occupying will can be reused for the next time new stack frame call being allocated for the new call. Okay, so we can say that stack memory is recycled aggressively and reused continuously. Recycled and reused. Recycled and reuse. This is how the limited stack size, we have limited stack size. Stack size is limited, but at the same time multiple function can it can hold the multiple function call. Okay, because we are reusing the same stack addresses again and again once the old function frame got deleted. Let me show you the stack size. This is the stack size our Linux kernel has 8192 bytes only. Now in the second demo we have seen that we are getting the different addresses every time. Okay, why different this time? Here in the second, from the main function we have called foo, and from this function we have called a function bar. Okay, so when the main function will be called, a stack frame will be allocated corresponding to the main function, and when the main is calling foo, where it has the local variable like y is stored here, return address stored here, CPU state stored here, a new function frame will be added. This frame is for main, this frame is for foo. Okay, it will have the value of x and the return address, and it is calling the function bar. So once the bar function will be called, a new frame will be added. So this has the value like z, return address, CPU states, and it is not calling any function, so it is returning after the execution. So we also have seen the downward direction growth of the stack frame because this has the higher address range compared to this. This is the lower. So from higher address range to lower address range we are moving. So we say that stack has a downward stack grows downward direction. So once this function will be called, because this is a nested call, so after the main, this is not getting cleared, it is calling one more function, so the address space is used, their address one space is used, their also address. So every time we are getting one new address, 1c 0 into 1a 0 into 08, like this. This is in used nested call, it has not returned, so new address will be allocated. This is calling the other function, till the time it will return, a new address will be given, and so once it will return, then only this address will be freed. If we call again, then maybe we get the same address. This returns, then only this address will be free and will be available to reuse. This is the reason we are getting different address this time. It is a nested calling. So we can say that function call life cycle is till the time it calls the return. Okay, once return is called, frame will be removed. Huh? This is calling return after the bar. So once the bar will return, it will call return. So then only it will get deleted. It print the address and return. After returning, this stack will be deleted. After the bar returns, it also returns. This will be deleted. Similarly, this will be deleted. So life cycle of a function call is till the time it returns. Okay. Let us. So this will be the main function stack. So this is the main function stack, and in the main function we are printing first, just know these addresses, registers. We have return here, return jump to main function, and from the main we have print, we are calling foo. Okay, so every time a function call will be made, we have a new frame, new locus, and new address space. So frames, new frame in the recursive call, frames kept on expanding. So stack size is expand, and in case stack limit is reached, we will have the stack overflow. In case stack limit is reached, we know that stack is a limited memory. So once the stack limit reached, we have stack overflow. This error we have mostly seen in case of recursive calls. Because of too many frames, stack exceeds its limit. So kernel eventually detect that invalid access and send sig es egv, sig's egv, segmentation fault, because our stack segment limit has been exhausted. So we can say the segmentation fault are actually from recursion are not the random crash, but it means that we have exhausted the stack size. Let me show you in the code as well. This is a function for recursive calls. In this, from the main function, we have called a function recurse. Okay, with some value. Okay, in the recurse, we have that value, and we are just printing the depth, whatever number we are getting, and the value of x, and calling the same function again by incrementing the value. Okay, without any return. Okay, we are not returning, we are just adding the frames. So let me compile it once. Segmentation fault. So we have called this from value 10,000 something, and till it reach the highest memory range, it crashes. Okay, so if you say how many frames has been added, this much. Every time a new frame is added, new address has been called, because we are not returning, we are just kept on calling the functions, and it exhausts the stack size, and we get the segmentation fault. So here segmentation fault from recursion is showing that we have exhausted the stack region, stack pointer. Stack pointer, which is SP. So what it mean by stack pointer? This is maintained by CPU first thing. By CPU. So this is a CPU register. Okay. Usually in the assembly we will see RXP. RXP. This stands for stack pointer. Okay. And it points to uh, top of the stack. Current top. So stack pointer, this is the stack pointer. If we have multiple function call where the current top exists, it will points to this. So from main, function 1 will be called, so function 1 frame, function 2 frame, function 3 frame. If currently the function 4 is being executed, stack pointer will be here. Okay, and we have second register, CPU register, that is base pointer. Base pointer, which we call BP or RBP sometimes. This is stable frame reference. Okay, useful for accessing locals, debugging and stack walkthrough. Like if our stack frame has moved from main function to this function, so it will kept on pointing to the stable location like main. Here it will kept on pointing. So we, from this base pointer, we will come to know, okay, how much frames has been added to this stack. So this is a something like stable. This is stable. So we say that stable frame reference. Base pointer is stable frame pointer or reference. We have seen the stack gives memory structure to execution, and memory in the stack segments are manually managed. Next episode, we are going to see the heap segment. In this case, memory is not manually managed but managed by the allocator and the kernel internals. What happens and how the heap segment memory is managed, we will check in the next episode. Stay tuned. Thank you.